thank you for inviting me back again and for giving me a second chance to show some of my favorite geometric constructions. Today, I'll be talking a little bit about constructions relating to the ellipse. Of course, everybody knows about ellipses as curves, and I'm sure that some of the elementary things that I'll be starting off with will be very well known, but there are different ways to attack the problem of the ellipse and to even define what it is supposed to be. And what I will be using today is an elementary synthetic approach. So the various things that I will be showing will not involve any kind of calculation and will not involve any kind of analytic structure. It's all purely synthetic and construction oriented. And I guess we can start off here by, I'll give you my screen first of all. I hope you'll be able to see this. And here we are. Okay, I hope you can see my screen now.
Yeah, we can.
Yes. So this is what I'll be talking about, some interesting constructions on an ellipse. And first of all, I want to start off with a definition of an ellipse. And of course, as I said, I'm sure all of you are familiar with some kind of a definition of the ellipse, but maybe not necessarily the one that I want. There are, I guess, three really well-known definitions and three different ways to attack the problem of the ellipse. There's the original classical concept of the conic section, of course, that it's a plane intersection of a cone. And that is certainly a purely synthetic approach that we could use. There would be plenty to show also if we were using that definition. The second is the purely analytic approach to simply define the ellipse by its equation. And I'm sure that you'll all be familiar with x squared over a squared plus y squared over b squared equals 1, or some variant of that in the plane, in the coordinate plane. Of course, these are equivalent definitions, and they're also equivalent to the definition that I'll be using, which I also assume that you'll probably be familiar with. The definition of an ellipse is the set of all points that have the property that the sum of their distances from two given points that we normally call the foci, the f1 and f2, is some constant, and we name the constant 2a. The reason that we use the 2a is because a line segment of the length a, of course, will play a role in the construction of the ellipse. And of course, it's the same a that we also know from the analytic approach. So there is the connection right there, right from the beginning. But this definition that I've written down here now is the classical approach that we can use for all constructions. And we can actually find all proofs of elementary, or well, all is probably overdoing it a little bit, but most proofs of elementary constructions simply by deriving them from this singular definition without any use of analytic methods. For certain proofs, analytic methods are much easier. So it is, of course, advantageous to show that the various definitions of the ellipse are all equivalent, and that we always get the same curve, no matter whether we use this definition or the conic section definition or the analytic definition. They'll always lead to the same point set. So it doesn't really matter where we start. But if we start in this way, we'll have this drawing that I have here on the right of the screen now. This shows the following concepts. We have 2 points, f1 and f2, that are already labeled as such. In the middle, we have their midpoint, the midpoint M of the line segment f1, f2. At the bottom of the figure, we have a line segment of length 2a, which has been divided by a point somewhere in between the two endpoints into two sections of length r1 and r2. And the idea here is that we can now derive a pointwise construction of points, of any random points of the ellipse, by simply choosing this point on the line segment of length 2a at random, and then using our compass to first draw a circle with radius r1 and midpoint f1, and then a second circle with radius r2 and midpoint f2. Both of these circles, or at least arcs of the circles, are shown in the figure. And where they intersect, we get 2 points. The points here are labeled P at the top and P bar at the bottom. And these 2 points then definitely have the property that is required of a point on the ellipse, because the sum of their distances from the 2 points f1 and f2 is equal to the sum of the 2 radii of the circles, of course, and that is exactly 2a, because we divided the line segment of length 2a into these 2 sections of length r1 and r2. Of course, we can use the same dividing point by exchanging the roles of f1 and f2, and then drawing a circular arc with radius r2 and midpoint f1, and on the other hand, an arc with midpoint f2 and radius r1, and intersecting those 2, that gives us 2 more points. Those are labeled here with p prime and p bar prime. So for each such point that we use to divide the line segment of length 2a, we get 4 points of the curve that all have this elementary defining property that we started out with. Looking at these 4 points, we immediately see that the curve that is defined in this way has various symmetry properties. For one thing, by exchanging f1 and f2, we see that we have simply exchanged the properties, or the roles, let's say, of the smaller circle and the larger circle. So that means that we've simply exchanged the points p and p prime on the one hand, and on the other hand at the bottom, p bar and p prime bar. So that means that the bisector of the line segment f1, f2 is definitely going to be an axis of symmetry of the complete point set. And similarly, of course, because f1 and f2 are the midpoints of all of these circles that we've been drawing, the line joining f1 and f2 will similarly be an axis of symmetry of the complete point set, for the reason that we always have another point at the bottom if we first construct one at the top, and the other way around as well. So we always have 2 points in which these circular arcs intersect, and since the midpoints are on this line of symmetry, the 2 points are always symmetrical with respect to this axis. Because we have 2 perpendicular axes of symmetry, we also have a centrum of symmetry. So the point that I have labeled with M is actually the midpoint of the curve, in the sense that it is the center of symmetry for the curve. We can reflect any of the points P that we've constructed, and we obtain the symmetric point. In this case, the symmetric point to P is P prime bar. So we will always have that symmetry as well. So the whole curve is very symmetric no matter what we do. And of course, we obtain a curve of this type that everyone recognizes. There's nothing at all unusual here in this whole concept. We see the vertices A and B as the main vertices. Then we have the minor vertices C and D, and those are the points of the curve that lie on the axes of symmetry. We simply name the axis of symmetry that joins the 2 foci, the main axis, and the one perpendicular to it, we name the minor axis. And the points of the curve that are on these axes are then the vertices of the curve. It is actually fairly straightforward to simply determine that the points A and B are found by taking the distance A and just drawing a circle with midpoint in M and intersecting and radius A and intersecting it with the main axis. If we consider the distances of such a point A from F1 and F2, the sum of the distances from A to F1 and F2 is then equal to the sum of the distances from A to F2 and from B to F2, because the distance from B to F2 is the same as the distance from A to F1. And therefore, since the whole distance from A to B is also equal to 2a, A must therefore have the same property as we require of all the points of the curve, and the same, of course, holds for B. The points on the minor axis, C and D, are just as easy to obtain, of course, because we simply know that any point on the perpendicular bisector of the segment F1, F2 is certainly a point that has the same distance from F1 and F2. So if this distance is equal to A, then both distances will be equal to A, and the sum is certainly equal to 2A. So again, we simply intersect the circle with, in this case, midpoint either F1 or F2 with the minor axis, and immediately obtain these two minor vertices, C and D, of the curve. So everything that I've said so far, I would assume that everyone is familiar with. Maybe not necessarily in exactly this way. If you're more used to an analytic approach, then you may not have approached it in this order. You may have started off with the equation and then simply consider what points fulfill the equation under the assumption that the major axis is the x-axis, the minor axis, the y-axis of the coordinate system. And then, of course, it's still possible to show that what we've used here as the defining property holds for all such points. That's another way to attack this problem. Of course, it's not the classic way. It's a more modern way, but it has, each of these methods of attack has certain advantages and disadvantages, of course. Now, once we've considered these basic ideas about pointwise construction and definition, we can advance to the next idea. And the next idea is to take a look at the tangents of such an ellipse and something called the Directrix circle. Now here we'll be coming to a property that maybe not everyone is familiar with. I don't know how much thought you've given to these types of problems in the past. What we have here in this drawing, or in this figure, is the following idea. We have 2 points, F1 and F2, given, again, the two foci of the ellipse. We have a point P that has already been constructed of the ellipse, so we know that the sum of the distances from F1 to P and F2 to P is equal to 2A. 2A, of course, also being the distance between the two major vertices of the ellipse that are drawn here on the major axis. So we also have the ellipse itself shown here, and we can see that we've also added the tangent of the curve in point P. Now, the question is, how can we construct such a tangent? It turns out that the tangent is simply the angle bisector of the two lines joining the point P with the two foci F1 and F2. And of the two angle bisectors, it's the one that does not intersect the line segment between F1 and F2. The one that does intersect the line segment between F1 and F2 would, of course, would be the line perpendicular to the curve in P. Now, the question is, why is this the case? Why is this exactly the angle bisector? And it's actually quite easy to prove why it's the angle bisector. We simply have to take a close look at what we've drawn here. We have a second point P bar on T, and if T is, we assume now that T is the angle bisector of the two lines joining P to F1 and F2 that I've named L1 and L2 here in this figure. And T, of course, as its angle bisector, we simply need to show that there cannot be a second point of the curve also on T. So I've chosen any random second point, P bar, on T. And we assume for the moment that P bar is also a point on the ellipse. If P bar is also a point on the ellipse, then it will then that will mean that T is a line that cuts the ellipse in 2 points, so therefore it's not a tangent. But we can show that this will lead us to a contradiction of our assumption that the P lies on the ellipse. Now, the reason for this is if P bar lies on the ellipse, then we know that the sum of the distances from P bar to F1 and F2 must be equal to 2A. We do know already that the sum of the distances from P to F1 and to F2 is equal to 2A. Now, we consider for a moment the point G1 that I've added here in the picture. The point G1 is the picture, the point symmetric to F2 with respect to T. So that's why there's a right angle that's noted here on the line orthogonal to t through f2, and the distance from g1 to this line t is equal to the distance from f2 to t. Of course, that means that the distances from p to f2 and from p to this point g1 will also be equal. G1 must lie on L1 because t, we've constructed t to be the angle bisector of the angle formed by the two lines L1 and L2. So that means that if we reflect one of the points on one of the lines on this angle bisector, then of course it will come to lie on the other of the two lines. So that means that this point G1 on the one hand lies on L1, and on the other hand, its distance from P is equal to the distance of F2 to P. Now that means that the distance from F1 to P plus the distance from P to F2, which we know to be equal to 2a, that was the defining property of P in the first place, is equal to the sum of the distances from F1 to P and from P to G1, because the distance from P to G1 is equal to the distance from P to F2. So that means that the distance from F1 G1 is also equal to 2a. That means that such points G1 that we obtain by reflecting the other focus of the ellipse F2 on any tangent or any, okay, for now it's not the tangent yet, but on any angle bisector of such of the lines joining points of the curve to the two foci. Such points will always lie on a circle with midpoint in F1 and radius 2a. That's the defining 2a of the ellipse, of course. Such a circle is known as the Directrix Circle, and we will find that using this Directrix Circle for constructions and for constructive purposes will help us to find all kinds of different things relating to tangents of the curve, and that will be very useful. We'll be doing several constructions to come next. We'll see how we can use this, how we can apply this when we want to do classical Euclidean constructions on an ellipse. Especially one such construction we'll do in quite a bit of detail. Now, we still haven't shown that the second point, P bar, can't be a point of the ellipse, but that's actually quite straightforward now. If P bar is a point on the ellipse, then the sum of the distances from P bar to F1 and to F2 must also be equal to 2a. Now, since P bar is a point on T, and therefore on the angle bisector of the angle formed by L1 and L2, that means that the distance from P bar to F2 is again equal to the distance from P bar to G1. It's the same property that we had for P, simply symmetric. So that means that the sum of the distances from P bar to F1 plus the distance from P bar to G1 must be equal to 2a. But we know that the distance from F1 to G1 is equal to 2a. We've already discovered that. And therefore, the sum of the distances from P bar to F1 and to G1 can't also be equal to 2a due to the triangle inequality. We have a triangle here. If P bar is not equal to P, then we have three sides of a triangle. Two sides are P bar F1 and P bar G1. And the sum of these two sides is certainly greater than the length of the third side being F1 G1. And that, of course, is equal to 2a. So that means that the sum of the distances from P bar to the two foci is definitely greater than 2a. And therefore, there cannot be a second point of the ellipse on this line T, and therefore T is indeed, as we claimed, the tangent in P. Now, this idea gives us all kinds of options now. The main thing that it helps us with is that this is the first of several ideas that we could have of how we can reduce constructions on an ellipse to constructions on a circle. And the reason that this is interesting is that, of course, if we're using Euclidean methods for our constructions, we're only allowed to use a straight edge and a compass. And with a straight edge, we can only draw straight lines, and with a compass, we can only draw circles. So although we may be able to draw as many points of an ellipse as we wish, and we may be now with this idea also be able to draw as many tangents of the circle as we wish, we still can't draw the circle, the ellipse, sorry, as an entire curve. So if we want to do things like intersect the curve with a line, or intersect the curve with some other curve, or find tangents of the curve through a point or parallel to a given direction, or all kinds of other things, we can certainly hope to find constructions that will make this possible. but we have to somehow reduce the constructions involving a circle rather than the ellipse itself. And one option that we now have is transferring these problems to problems involving these directrix circles. There are, of course, two such circles. The one that we have here now in play is the one with midpoint in F1 and radius 2a. But of course, we could exchange the roles of F1 and F2 rather than reflecting F2 on the tangent. We can reflect F1 on the tangent, and then of course we'll get a different such point that will have the distance 2a from F2 and therefore lie on the second directrix circle with midpoint in F2 and radius 2a. It's completely interchangeable. Doesn't matter. Sorry about that. It's completely interchangeable which of these two circles we want to use for our constructions. They're completely equivalent. We just have to be careful which of the foci is the midpoint, and therefore which of the other focus will always be the one that is symmetric to the point that we can use for the construction with respect to the tangent that we want. So having said all of that, I'm going to leave the PowerPoint presentation now for a second, and I'm going to go to something here in Geogebra, not what I have right now, but rather I'm going to start something else. I have here a situation of the type given that I was just talking about. What I have given here in this situation is an ellipse, which is given by its two foci, F1 and F2. So these are the 2 points, F1 here, F2 here. The midpoint of F1, F2 is this point that I've called M. I also have the length of the line segment 2a given in that I've given the two main vertices of the ellipse with A and B, A over here and B over here, by simply determining points that are the distance A from M. So M is the common midpoint of the two line segments F1, F2 and AB. And with that, of course, the ellipse is given, at least from a theoretical perspective. We know now how to construct all the points that we want of the curve. We know how to construct tangents of the curve if we want. We have all of these various options on how we can continue our construction. And what we want to do now is determine the tangents of the ellipse with their points of tangency to the ellipse that pass through this given point P over here. So P is not a point of the ellipse, it's just any point of the plane, anywhere. It's, of course, required that we choose it outside of the ellipse. If we choose it inside the ellipse, then there are no real tangents of the ellipse passing through the point. If you're, maybe some of you will be a bit familiar with analytic methods of working with such things. And if you have ever calculated tangents of an ellipse through a point, then you know that choosing the point in the interior of the ellipse leads to complex coordinates. So it is possible to argue that there are conjugate complex tangents through such a point if it's in the interior, but that is not something that we would normally consider to be an elementary Euclidean construction. It is possible to construct things with straight edge and compass that also solve problems in such a case, but then we have to define what it means to have complex tangents and things like that. Those are things that are actually, of course, not, since they're not real, they're not actually visible, and then we need some additional definitions to work with these things. That goes far beyond the scope of what I have planned for today for just a 1.5 hour talk. But of course, it's a very interesting topic, something that also will not necessarily ever turn up in a mathematics competition that I would know of, but all of these things that have to do with extending real geometric properties in the Euclidean plane into a complex extension of the Euclidean plane are actually quite fascinating, and working on constructions in that area is actually quite an interesting topic in itself, but of course a huge topic that we could talk about some other time. Now here, in order to apply the knowledge that we have, we can argue the following. If P is supposed to lie on a tangent of the ellipse, we know from the figure that we were just looking at earlier that every point on the tangent is a point on the angle bisector of the two lines that are formed by joining the point of tangency with the two foci of the ellipse. And we know that if we reflect one of these two foci on the tangent, then we obtain this point that was labeled G1. In German, the reason that I labeled it with G, that has actually to do with the German usage. In German, such points are called Gegenpunkt. That would start with a G. In English nomenclature, as far as I'm aware, I don't think that there's actually a word that describes the same thing as the German usage of the term Gegenpunkt. It would be something like a contrapoint or a counterpoint or something like that. But I haven't ever seen it in the English language literature used at all in that sense. Maybe somewhere there is a term used for these points, but in German it's actually quite common to have a word for it. I don't know, it's always interesting comparing German usage to English language usage in these geometric things, because some of the elementary things can be quite different. Of course, the more complex things that are more modern tend to be identical in more or less every language, but these elementary things that go back historically can be quite different. Okay, so anyway, we know that such a, let's call them counterpoint for now, must lie on the Directrix circle, and the Directrix circle has the radius 2a, and as a midpoint, one of the two foci, I'm going to use F1, the same as we had in the earlier figure. So I'll simply draw such a circle with radius 2a and midpoint F1. And I now know that the point P must be equidistant from the other focus F2 and from this counterpoint. So that means that the counterpoint must lie on the circle with midpoint P that passes through F2, because all points on that circle have the same distance from P as F2 does. So that means I simply have to construct this second circle here, this circle. And I now have two possible options for such a point that I labeled as G. Those are the 2 points where these 2 circles intersect. It's, of course, the 2 points of intersection are completely equivalent. They play the same role in our construction. There's no difference at all. But if I intersect them now, intersection is there. We have one here and one there. And I can label these 2 now, just so we have a name. We'll call one of them G1, the way we had it earlier. And the other one I'll call G1 prime. So it's the second one, the alternate one. So G1 is up here and G1 prime is down here. Oops. There we go. Okay, and now having done this, we know that the tangent of the ellipse passing through P with this point up here, G1, as the symmetric point to F2 with as relates to the tangent, is simply the bisector of the line segment F2 G1. Now I can either draw this line segment and then determine its midpoint and then join the midpoint with P, or I can immediately draw the line perpendicular to this line segment through P. Of course, P has to lie on the bisector because the distances from P to F2 and from P to G1 are equal. That's the whole reason that we used the circle over here. So if I simply draw the line perpendicular to P1, I obtain the first tangent that I need right here. So this line that I've just drawn, we'll call it T. I'll just call it T. We don't need anything else really. This is the first tangent of the ellipse through this point P. And the point in which this tangent actually is tangent to the ellipse, of course, must now be the radius of the Directrix circle that passes through this point G1. So if I connect F1 to G1 and intersect that with T, then this point here must now be the point where they join together. So this is the point of tangency. I'll call that capital T. So this is the point of tangency. Of course, I can do the same thing on the other side with the other point, G1 prime. It's exactly the same thing. At first, I simply joined the focus F2 with this point G1. Now I can join F2 with G1 prime. And then the tangent through P will be perpendicular to this line segment. So this is our other tangent. Maybe I can clean things up a little bit. Put P over here and B up here. So this is the other tangent. We'll call this T prime. There we go. And the point in which T prime is tangent to the ellipse, of course, again, is simply the point where it intersects the radius of the directrix circle through G1 prime. So once again, I'll simply draw the radius here. Once again, I have to not want to do that. This is a little bit nicer. Okay. And then the point of intersection is here. And this is my second point of tangency. So we'll call it T prime. Now we know that these are the points of tangency and that these are the two ellipse tangents through D because of the properties that we had a look at earlier. But of course, it's a nice idea now to take a look at the ellipse itself and see whether these actually are the tangents of the ellipse. And of course, Geogebra allows us to immediately draw the ellipse without any further constructions. This is obviously not a Euclidean construction that I'm doing now. To use the conics tools in Geogebra is probably as far away from a Euclidean construction as you can get, but it's something that Geogebra offers us as a purely, let's say, descriptive tool. It's a nice drawing implement, but of course it's not a constructive implement. It's not a Euclidean construction in any sense. But if I simply click on ellipse here and then click on the two foci and one of the points here, then we immediately see that these 2 points T and T prime are indeed points of the ellipse, and that the two lines T and T prime are the tangents in these 2 points, as of course they had to be because of the defining properties of the ellipse that we had to look at right from the start. Now, I think it's fairly easy to imagine that similar constructions will be possible if we vary the situation a little bit. For instance, if we're not looking for tangents of an ellipse through a given point, but rather tangents of an ellipse that are parallel to a certain direction or parallel to a given line. That is another construction that we can easily solve with such a method. We simply have to, again, consider what has to hold for such a thing. And if we consider that the direction of tangent is given, then we can simply draw the line perpendicular to that direction, which doesn't really matter where the line is, through F2, intersect with the directrix circle, and we'll get the possible points G1 and G1 prime in a very similar fashion. It's essentially the same construction, of course. If for those of you familiar with projective extensions of the Euclidean plane, you'll of course recognize the concept of simply putting the point P at infinity, and then of course we have the right angle because it's essentially the same thing as drawing a circle with an infinite radius. All of those things are, of course, metaphorical. If we put it that way, it's not actually there's no such thing as a circle with infinite radius. But if you consider a line perpendicular to a direction as such a thing, then it all makes sense in the context of extending the Euclidean plane to the projective point. So that is something else that we can look at. Now I'm just going to save this for now because I was asked to send it, so I'll just save it as it is. And then we'll return briefly to our PowerPoint. This is where we were earlier. We were talking about the tangents in the directrix circle, and now I'd like to move on to another concept, that is to the affine transformations of a circle. I mentioned from the outset when we started with the concept of the directrix circle that we require some kind of a connection between the ellipse and a circle in order to be able to use this circle that results to apply Euclidean methods in our constructions. And the concept of the Directrix circle is one option that we can use. Now, there's another idea that is also an option here. Second, there are many, but this is a second idea that we'll be introducing now. And this concept is to apply an affine transformation to the ellipse and to do it in such a way that the result is a circle. And there are many ways to do this, but a very elementary way is the one that's suggested here in this drawing. As you can see, I've actually written down something analytic here, that we have a circle, which I've called K. The reason that it's called K is because this was originally drawn to be used in a German language context again, and in German, the word for circle starts with K. It's Kreis. I don't know if any of you know any German, but that's why. Otherwise, I wouldn't have called it K. But of course, it's a circle with radius A. It's simply a circle that has the same midpoint as the ellipse, and it's in the simplest spot that's possible in the Cartesian coordinate plane. So we have the midpoint of the circle equal to the midpoint of the ellipse in the origin, and we have the axes of the ellipse on the coordinate axes, with the main axis being on the x-axis, the minor axis on the y-axis. And we now have the concept that we can apply an affine transformation that leaves all of the points on the x-axis, that is on the main axis of the ellipse, fixed, but that transfers points that are not on the x-axis in such a way that the minor vertices of the ellipse are mapped onto the points that are a distance a from the origin and lie on the y-axis. So that would mean this point up here. That would be one of these 2 points that one of the two vertices, minor vertices, map onto. It doesn't really matter which one. Usually we use the top one to map to the top, but it can be the other way around as well. It doesn't really matter. And this bottom vertex will map onto this bottom point of intersection of the circle. So of course, that means that we have 4 points equidistant from the midpoint on the 2 axes. They're all distance a from the origin. We have the 2 main vertices of the ellipse that are fixed points, and we have these 2 points that the minor vertices map onto. And it's actually quite straightforward from an analytic standpoint to show that the points of the ellipse then map onto the points of the circle with midpoint in the origin and radius a. But it's also possible to prove this with elementary Euclidean methods through similar triangles. I'm not going to do the whole proof now because it takes several minutes to do, and I want to get on to some more interesting constructive things. But maybe you want to try it on your own to actually prove that such an affine transformation exists. And actually, the constructions that we'll be using in the next drawing that we'll be doing together will actually apply the kinds of triangles that you need to use to do the proof. So the basic idea will be contained in the construction. So it's hidden a little bit, but it's easy enough to find if you take a closer look. So the idea here is that every point that of the type that I've called p bar here, of course, which is a point on the ellipse, will map onto some point p on the circle with coordinates x, p, y, p, but we won't need the coordinates for what we're doing here. So each point p bar on the ellipse maps to a point p, and the line joining them will always be perpendicular, in this case, to the x-axis, to the line that is pointwise fixed for this specific affine transformation. Now, if we have a look at this, that means that we can actually derive an alternative pointwise construction of the ellipse from this idea. This is sometimes known as the concentric circles construction of the ellipse, and I'm sure that many of you are familiar with this. The basic idea here is simply that there are 2 different such affine transformations that will transform the ellipse to a circle. The one is the one that I've just talked about, using the x-axis or the main axis of the ellipse as the axis of the affine transformation. That will map this point P of the ellipse onto this point that I've called PA up here on this outer larger circle with radius A. And there's a second one that we can also obtain by leaving the minor axis of the ellipse fixed, and again mapping on right angles, and in such a way that the major vertices of the ellipse are mapped onto points that are the distance b from the common midpoint. And then we obtain as a map of the points of the ellipse, the points of a circle with radius b. That is, of course, the minor axis length of the ellipse. And since in one case we're extending the point P vertically by a factor of A over B, and in the other case horizontally by a factor of B over A, these 2 points PB and PA that result here from P lie on a common radius of these 2 circles. And these are, of course, concentric circles, and these points lie on the same radius. So that means that we can obtain it by simply turning around this whole construction and doing it in the opposite direction. We can obtain any point P on the ellipse by simply drawing 2 circles, 2 concentric circles, the smaller one with radius B, the larger one with radius A, then choosing any common radius of these 2 concentric circles, choosing the 2 lines that we want to be the axes of our ellipse, and then drawing the lines perpendicular to what should be the major axis through the point on the outside circle and through the point on the perpendicular to the minor axis through the point on the smaller circle, and where they intersect will certainly be a point of the ellipse. This construction was described in the literature in, I think it was the 18th century, I think that's correct, by a French mathematician and geometer named Geretschlaegar. And in German-speaking countries, the construction is actually called the Geretschlaegar construction, named after Monsieur Geretschlaegar. In English nomenclature, it's normally called the concentric circles construction, after simply descriptive nature of the construction. That's at least, I think, the most common name for it. It's actually very simple, and it's the first of these applications of how we can connect these circles, these concentric circles, these circles that are concentric with the ellipse because they have the same midpoint, with the circle itself. Now, of course, we can also use this idea to do constructions of the same type that we did earlier. And I'd like to show an example of such a construction. If we look here, I think you may have the same problem here. I can move this. Okay, I can move this over here. If you just have a short look at this, we're going to be doing this construction next. The idea here is simply that we have an ellipse given, and we have a line G given, and we want to determine by use of Euclidean constructions the common points of G and of the ellipse, these 2 points P and Q. Obviously, if we just do this in Geogebra, there's nothing to do, because we just let Geogebra draw the ellipse, and we just go on points of intersection, and then we immediately have the points of intersection. But that's not a Euclidean construction, because we don't know all of the points of the ellipse. We know them in theory, but we don't know them in practice. So actually what we have to do here is to do some constructing. That's the next thing that I'd like to show here. We will go back to our Geogebra, move this back to the right, and now start something new. Let's try this one here. And here we have exactly such a situation given as I just described earlier. We have an ellipse given by, again, as before, 2 foci f1, f2. We have the length of the line segment AB given. So it's the same as before. And then we have this line L, and we want to find, first of all, the common points of L with this ellipse. Now, as I mentioned, if I do this in Geogebra, it's trivial. There's nothing to be done, because I simply go on the points of intersection, and then I can click on the ellipse. Okay, I could if it was doing this properly, but for some reason it's not. Let's get rid of that again. Let's try it again. Okay, I click on the ellipse, I click on the line, and then I immediately have the 2 points of intersection, right? But that's something that is not Euclidean. So we'll get rid of the ellipse altogether for now. And we'll just say, okay, we don't have the ellipse for the moment. We'll be able to use certain points of the ellipse for the construction, but we don't have it as a complete geometric object at our disposal that we can actually use constructions with. We can construct all of the points of the ellipse that we want. We can construct specific points of the ellipse if we want, but we can't use the whole ellipse as one geometric object. So what can we do? Okay, we know that there is an affine transformation that transforms this ellipse to the circle with the same midpoint as the ellipse and with the radius a. So first of all, I can draw this circle. And of course, it will be possible to determine the common points of any line with this circle. But the common points of this line with the circle won't transform to the points that we want, because they won't transform the points on that line at all if we use this affine transformation. So what we have to do now is consider the points of L to be points in the point set relating to the ellipse, and we have to transform these points to the point set relating to the circle. And to that purpose, we'll need one point of the ellipse that we know transforms to a specific point on the circle. And of course, for that purpose, we've already mentioned that we can use one of the minor vertices. Now, determining a minor vertex of the ellipse, that's an elementary thing to do. We simply intersect the two circles with radius a and midpoints f1 and f2. That's a very elementary thing to do. Of course, we could also intersect them with the perpendicular bisector of f1, f2, but I'm going to do it here with the two circles. So I have this circle and this circle. These are the two circles with radius a. Perhaps if we make them red, all of this stuff will be easier to see later on. So I'll just change the color to red here. So these are simply the circles that I'm using to determine the minor vertices of the ellipse, where they intersect these two circles. I have the two minor vertices. So this one here is the vertex C, and this one here is the vertex D. Right now, I'll only be using one of them. So I'll just label the vertex C. That'll be enough. We won't need D. And doing the affine transformation, we know that this point C will map onto the point that lies on the line perpendicular to the major axis of the ellipse. So the line F1, F2, or the line AB, however we want to consider this, and also that lies on this circle. So all I need to do is determine the point where this is the perpendicular, of course, because it's the line joining these 2 points. And where this intersects the circle is the point C prime. It's the point that C maps to in this mapping of the ellipse to the circle. So I can intersect here, and this point of intersection is then the point C prime. Now, if we want to find the line L prime that the line L maps to, we can then intersect L prime with the circle. And once we have those points of intersection, then we can return them to the point field of the ellipse by simply drawing these perpendiculars to the major axis. So as soon as we've found this other line L prime, we're done. And the question arises now, how do we find this other point L prime if all we know is this point pair C and C prime? And the reason that we can immediately obtain the line L prime with the help of C and C prime is the fact that any affine transformation will always map parallel lines to parallel lines. So that means if we take the line parallel to L that passes through C, which of course determining a parallel line is a Euclidean construction. So we get this point here. I'll do anything that we do in the construction now in this sort of light blue. That makes it a little bit better. So this is now a different line. It's not L itself, but I'll call it L bar. this parallel line L bar. That since this point passes through C, we know that the line L bar prime in the circle field will then therefore have to pass through C prime, because C will map to C prime. And also we know that the point where L bar intersects the major axis of the ellipse, which is this point down here, this point, that point does not change under the affine transformation, because the whole major axis of the ellipse is pointwise constant, is pointwise, is made up of fixed points of the affine transformation. So that means that this line L bar maps to the line joining this fixed point with the point C prime, which is the map of C under this affine transformation. So that means that it maps to, again, maps to this line here, which once again, I will make this color. And this is this being the map of L bar, I'm going to call it L bar prime. There we are. Now, since L bar maps to L bar prime and parallel lines map to parallel lines, the line L, which is parallel to L bar, must map to a line that's parallel to L bar prime. So that means I can simply find a parallel to this line somewhere. And I know one point of the line that L must map onto, because once again, I have the point of intersection of L with the major axis of the ellipse, which is another one of these lines that is made up of another one of these fixed points of the affine transformation. So if I intersect here, I know that this point here of intersection must be another fixed point. That means that L must map to the line parallel to L bar prime through this point here. So therefore, if I construct the parallel line to L bar prime through this fixed point here, I obtain the line L prime that I required. That was the thing that I needed the whole time. That was what I was chasing after. So this is L prime. That's this. Now, what's the great thing about L prime? Well, L prime, of course, is now the line that L maps onto under this affine transformation. And since we know that the ellipse maps onto the circle, this black circle that I have drawn here, with midpoint M through AB and of course C prime also, we know that the points of intersection of L with the ellipse will map onto points of intersection of L prime with this circle. And of course, those are known because it is a standard Euclidean construction. It's allowed in Euclidean constructions to determine the points in which a line intersects with a circle. And these are both things that we've constructed with our standard Euclidean methods. So therefore, the points of intersection can be considered known under Euclidean standards. So we know this one point of intersection and this other point of intersection. We'll call them maybe P and Q. So good enough names. We'll call one P and the other one Q. Well, actually, probably, no, let's do something different. Let's call it P. Let's call it P prime because this is in the circle area. We'll call the other one Q prime. We'll call the ones P and Q that are actually in the circle field. So this one's P prime up here, and this one is Q prime down here. And if we know that P prime is here, then it's easy enough to find P now because we know that P is simply the point on L where the line perpendicular to the major axis of the ellipse through the point P prime intersects. So we simply need the line perpendicular here and intersect that with L. That gives us this point here, and that point will then be P. That's the point that we had immediately when we did it with the Geogebra methods, but by Euclidean methods, of course, we had a little bit of a detour to go before we finally found the point, but it was still straightforward enough. And the same thing, of course, holds for Q. If we know Q prime, then we simply determine the line perpendicular to the major axis through Q prime and intersect it with L. It's the same thing. This line here intersected with L, and that gives us the point Q. That's right there. And once again, if we now reintroduce the ellipse, which of course is once again sort of cheating, but just to illustrate what we've done, these will be the same points that we had earlier where we just did it with GeoGebra methods. If I now allow GeoGebra to draw the ellipse again, we'll see that these points actually do lie on the ellipse. P and Q are right on the ellipse, and of course they're on L anyway because of the way that we did the construction. They have to be points on the ellipse because we've used the affine transformation to construct them, but we did it in such a way that we also kept the property that they were also points of L, and of course that was something that we wanted to use in this context. Now, there are other things that we can also use this for, and we can also apply such a concept to the idea of transforming the whole thing and finding tangents parallel to a given line, for instance. And this is actually something that we can now simply add to this drawing, to this figure. We don't have to start all over again, but maybe I'll do this in a different color just so that we can see that, that it doesn't get all mixed up with these other things. But if we want to determine the tangents of the ellipse that are parallel to the given line L, we can make a following argument. We can say tangents of the ellipse parallel to L will transform under this affine transformation to tangents of the circle, the big circle that we're using, that are parallel to the line L bar. Now L prime. Now we already have L prime. You don't have to determine that anymore. And it's straightforward enough to find tangents of a circle parallel to a given line by simply drawing the radii of the circle orthogonal to that line, and where they intersect the circle are the points where we immediately know that the tangents will touch the circle. So all we need to do here in order to find the tangents of the circle parallel to L prime is simply to construct the line perpendicular to L prime through M. That's this here, but as I said, I'll do this in a different color so that things don't get mixed up. Let's do this green. We haven't used green yet. So this is perpendicular to L prime. If I intersect this with the big circle that we're using here, I'll get 2 points, one over here and one over here. I'll just do the construction on one side, but maybe on this side over here, we have a point of tangency, and we'll call this point over here T prime. The other one is symmetric, so as soon as we've done the construction for one, we can find the other one by means of symmetry. We don't need to do the construction twice. So this point T prime is the point in which the parallel tangent to L prime of the circle touches the circle over on this side. And of course, the tangent itself is either parallel to L prime or again, perpendicular to this green line. It doesn't really matter how we construct it, but I'll just click on the perpendicular line here, make this green again. So this line here is now the tangent parallel to L prime of the circle. Now I can name this tangent T prime. There we are. And knowing T prime means that we now immediately also know the tangent parallel to L that this point, that this line T prime maps to if we do the inverse of the affine transformation and transform back to the ellipse point field, because we already know that it will be parallel to L, and we also know that the point in which T prime intersects the major axis must be fixed again, same as we've already used several times. All of these points on this line are fixed points of this affine transformation. So this point doesn't change. That means that t prime will map onto the tangent t of the ellipse through this point and parallel to L. If I just now construct the tangent parallel to L through this point, this is a tangent of the ellipse. We immediately see that since I've left the ellipse there, that this indeed is a tangent of the ellipse. So this is now, make it green as well, just so that we see that everything that relates to this is green. It is the tangent. It's the tangent that we're going to call T now. Tangent of the ellipse that relates to this tangent T prime of the circle. And in order to find the point of tangency, well, that's very easy. We know that that's the point that this point T prime maps onto when under the inverse of the affine transformation. And that just means, once again, drawing a line perpendicular to the major axis of the ellipse through T prime and intersecting it with the tangent. That immediately gives us the point of tangency. Same argument as before. So it's just this perpendicular line here and intersect it with the tangent. And that gives us the point T right there. It's the point of tangency of this. Pull this out a little bit, make it a bit nicer. I already mentioned the other ellipse, the other tangent on the other side that's also parallel will simply be symmetric now. The two tangents of an ellipse that are parallel to each other, and therefore parallel to a third line, in this case parallel to L, but they're also parallel to each other, of course, are always point symmetric with respect to the midpoint of the ellipse. The whole curve is symmetric with respect to the midpoint, and any reflection of a line on a point will always result in a parallel line, and any reflection of a tangent will always result in a tangent of the ellipse. So that means that we simply get that symmetric in this case, and that means that we can simply do the reflection here, and that's also something that we can do automatically in GeoGebra. That's something that's again a little bit of cheating now. I'm not doing this in the Euclidean way, but the actual Euclidean construction of such a pointwise reflection is also not difficult. It's just simply joining the points with a line, extending it, and then using the compass to transfer the length of the line segment to the other side. So it's essentially the same thing. But here, of course, I can cheat. I can simply use the tool that gives me the symmetric point. So this is the symmetric point to T. That would be my T bar if I called it that. And reflecting the line T on the midpoint then gives me the tangent over here. So that's a cheap way of finding this by using GeoGebra methods, which of course is one of the nice things about GeoGebra, that we get a lot of things that that could be Euclidean, that could require Euclidean constructions in a much quicker way. But of course, we can also get things that cannot be done by Euclidean constructions in GeoGebra, and it's always useful to delineate those things, to consider what is now actually replaceable by elementary Euclidean methods and what isn't. As long as we're in these areas that we're using now, where we can reduce everything to circles and lines, then we can always do everything with Euclidean methods. That's essentially the trick in any kind of constructive geometry that reduces to Euclidean constructions, is always the question of whether things can be reduced to solving things to linear or quadratic constructions, because anything linear can always be done with lines, and anything that's quadratic can always be done with circles. It can always be replaced somehow. Sometimes it can be relatively difficult to do this, because there are some quadratic concepts that can be introduced in an algebraic way that can be very simple from an algebraic point of view, but are very complicated from the point of view of a Euclidean construction. But they can always be done somehow. There's a general proof that's actually fairly straightforward but long for that. But it's always possible, and the fact that it's always possible means that we can always search for these, but it's always a matter of how useful will that be. What are we actually discovering when we do these constructions? Okay, so much for this drawing now. The next thing I'd like to return, I think we still have a little bit of time. Yes, it's just been a little bit over an hour. I would like to return to PowerPoint again. Just back up here. There we go. And okay, so we've just considered this, and now I'd like to go on to consider the circles of vertex curvature. This is a third concept that will be shown to be quite useful. The circles of vertex curvature are something very interesting in working with ellipses anyway, because they are also aesthetically quite pleasing, and the special properties of these circles are not just elementary and not just of a Euclidean type or of a basic Cartesian type, but they are also important with respect to the properties relating to differential geometric considerations. So these circles and anything that has to do with curvature, of course, has something to do with properties that can be derived somehow from some kind of calculus in some way, and anything that has to do with calculus in such elementary things will always have something to do with differential geometry. So the fact that we're heading in this direction now with these next constructions is not surprising, but to actually do the calculations involved, that requires quite a bit of knowledge that goes beyond standard, what I would consider to be standard school knowledge. I don't know, maybe the school system in Nepal is different from here in that respect, but our students here, our high school students, definitely don't ever hear anything about differential geometry at all. They do learn some elementary differential calculus in the higher grades, but differential geometry is not even touched on. And it's not even something that most mathematics teachers would be aware of or work on in their studies. Of course, professional mathematicians, of course, will know all about it. But also, again, only if they either work in higher level geometry or if they work in analysis that requires differential geometry or knowledge of differential geometry. But the basic idea has something to do with this construction here. It's a very elementary construction. What is shown here is simply an ellipse with the vertices. I have one more C's to go. There we go. We have one of the major vertices B on the right and one of the minor vertices C on top. And what I've added here in this figure is the tangent of the ellipse in the main vertex, major vertex B, and the tangent of the ellipse in the minor vertex C. These two tangents intersect in the point I or 1 or whatever you want to call it. It was supposed to be a Roman numeral 1 when I wrote it. We can consider it to be I. And if we now join the 2 points B and C and then construct the line perpendicular to the line joining B and C that passes through this point I or 1, then it intersects the axes of the ellipse in points M and N. And these points M and N are the midpoints of circles that very closely approximate the ellipse itself. If we have a look at what's going on here on the right, I have 3 different pictures here that are all of the same situation. I have 4 points, A, B, C, D, with the lines joining them. In the first picture, I have an ellipse with the major vertices A and B and the minor vertices C and D. In the second picture here to the right of it, I also have this same ellipse drawn. It's drawn with a thinner line, so you can only see small parts of it here in between the circle arcs, but it's still drawn. The complete ellipse is visible in this picture, even if you have to look very closely to be able to see it. But in addition to the ellipse, there are 4 circular arcs. And the arc here on the right is an arc with midpoint in this point M that I've constructed over here that passes through B. I didn't label the point M here, but that would be the midpoint of this circular arc. And the other small circular arc on the left is symmetric. So it has the same radius, and the distance of the midpoint to this point, to this vertex here, is the same as on the right. And on the top, we have the same thing analogously. Of course, it's easy to imagine. This is another circular arc that passes through the point C, but that has its midpoint in the point N that was constructed over here. So N is a little bit below this other minor vertex here. And if we then draw this circular arc up here, then we obtain this arc at the top, and the bottom one is again symmetric with respect to the major axis of the ellipse. Now, in this drawing at the bottom, I've left the 4 arcs and eliminated the ellipse itself. So we only have the 4 arcs here. And if you look at this bottom drawing, you can see that even though there is no ellipse in this picture at all, it still looks like an ellipse almost. It's easy to say that the ellipse is approximated very, very well by these 4 circular arcs. And that's one of the interesting advantages of the circles of vertex curvature that have been constructed here. These circles are so close to the ellipse itself when you stay close to the vertices where they are tangent, that you can actually use them for drawing purposes. If for some reason there's ever any reason to draw an ellipse or to approximate an ellipse using only straight edge and a compass, it's actually very easy to draw these 4 circular arcs. And just with these arcs, you almost have the ellipse drawn, and these are precise. So it's not like drawing something just freehand or something like that. It's easy enough to fill in the blanks in between. So once you have the 4 arcs, you can add in these little curvy parts that I have here in the top right just by hand. And that's a very good approximation of any ellipse that you might require if you're drawing this on a piece of paper. Of course, if you're drawing with a computer program, then computer programs can do completely different things that are much easier. But if you're drawing by hand, this is actually a very good way to do the approximation. Now, the reason why this is so close to the ellipse itself in each case is simply given by the fact that these circles result by choosing any circle with a midpoint on an axis of the circle and moving this point in such a way that the points of intersection of the circle with the ellipse all coincide. If we consider this picture again here that's over on the left, if we consider this point M to not be where it is, that it's not constructed here, but rather more further on to the left, somewhere here where I've put the cursor right now. Okay, the cursor disappears again, but I've brought it back. So if I consider this cursor to be the midpoint of a circle, it's disappearing, this to be the midpoint of a circle that passes through B, then I'll get a circle that's larger, and that will intersect the ellipse in 2 more points, up here somewhere and down here somewhere. There'll still be a double intersection in B because the circle and the ellipse will have a common tangent here in B. So that's worth 2 points in some way. You can always say that if 2 curves have a point in common and also the tangent in common in that point, then they have 2 points that are infinitely close together. That's already a concept that some of you may be familiar with, because it's a concept from the area where analytic algebraic considerations of curves begin to meet considerations of differential geometry. This moving things close together so that they are infinitely close, and then considering the combinations of these things anyway. Those are essentially they're naive ways to put things that can be stated in a more precise way with methods of or using the notation of differential calculus, and with the methods of differential calculus, these things can be made more precise. But for now, it's close enough for us to simply say that we can move this point close enough to get all of these points of intersection to move together infinitely close, so that they all coincide. And then we have 4 coinciding points of such a circle with the ellipse. And when a circle has 4 such common points with an ellipse, we say that the circle and the curve hyperosculate. That's a special consideration that can actually only happen in a vertex. or in an apex actually, we want to be precise about this, of a curve. In any other point of the curve, such hyperosculation isn't possible. In general, if you just move points together, the best you can get is 3 infinitely close common points, 3 coinciding points of intersection. And such a thing is then just called oscillation. And if you have more than oscillation, it's then called hyperosculation. And because such a thing is possible in the vertices of an ellipse, we get these circles that have these wonderful properties that they approximate the curve so closely from a graphic viewpoint. Well, this isn't actually anything useful for a construction of anything in addition to just drawing the curve, but we will be able to use this in such a way. And this will actually introduce the third method that I wanted to show today, what we can do in these various ideas, and that is to say, how else can we translate or map an ellipse to a circle in such a way that the constructions we want to do on an ellipse will map onto the circle, such that we can do the constructions with Euclidean methods. And we can do that by using such a circle of vertex curvature. That's a third method. It's, again, not the only one. These 3 methods that I'm showing today are by far not the only ones, but they're, I guess, in some way the most interesting because they're the most different from each other. Other methods are sort of similar to one or the other, and these are really radically different methods in their own way. But they allow for so many different types of constructions to be done afterward. And this means that we can do the following type of a construction. Here in this drawing, I have an ellipse drawn here called L, and I have a circle in here, which is exactly such an ellipse, such a circle as we constructed earlier. So this is a circle that hyperosculates the ellipse in the main vertex A. And we can now consider the following fact. There exists a collinear transformation, not an affine transformation, but a collinear transformation that maps this ellipse onto this circle with the following properties. And now we have to know a little bit about collinear transformations. That's a little bit different, and I'm not sure that all of you will have used collinear transformations, especially not for actual constructive methods. You may be familiar with collinear transformations in linear algebra, and you may have studied them from a viewpoint of matrix transformations. But that's something that we're not looking at all right now. We're looking at purely constructive methods that produce 2 Euclidean constructions. And if we want to do a collinear transformation in this way, we can consider something called a perspective collinear transformation. That means that once again there is a line that is made up of all points that stay fixed under the transformation, and there's also a center of the transformation such that all pairs of points that map onto each other under this transformation pass through this common center. And when we have this collinear transformation that maps the ellipse onto this specific circle, the collinear transformation is always such that the center of the transformation is in their common point. So that's exactly in the point where they are tangent to each other, and their common tangent that I've labeled A here is then what I would call the axis of the transformation. That is the line that stays fixed pointwise under this collinear transformation. So this point P over here of the ellipse will map onto this point P bar of the circle, the same as this point B, the other major vertex of the ellipse, maps onto this point B bar of the circle K, which is simply the diametrically opposed point to the common point A of the 2 curves. Using this, we can do all of the constructions that we also considered with the affine transformation. So we also have the opportunity to do this here. And I'm just looking at the clock. I think we still have time to do one such construction, and this was what I was hoping that I would still be able to do, and I think that we still have the time to do this. I may have to rush through it a little bit, but I think it's worthwhile to have a look and see what these types of things look like. And what I would like to do now is revisit the construction that we did earlier, where we had two foci of an ellipse given, and the two major vertices, plus a line. And we wanted to determine the tangents parallel to the given line of the given ellipse. And I want to show how that will be done using this collinear transformation. And that's actually quite a fascinating construction. As I said, I may have to rush through this a little bit. I hope you don't mind too much, but I think we'll be okay by doing this. What we'll do now is simply to start something again. Yes, we'll start with this. No, I've saved it. Okay, no, I won't be able to do this. So we'll have to start over again. Okay, so what we'll do now is we'll simply start with the following concept. We'll have this. I'll make it a little bit easier on us now, because we don't have a whole lot of time left. I'll start off with the midpoint and the two major vertices, and I'll also give us the minor vertices here. That will make it slightly easier to do this whole construction. So what we have given here right now is the point A, B, C, and D of an ellipse. So A is down here. B is over here. C and D. I will add a few lines here. This line perpendicular to it, which it does not accept. There we go. The line perpendicular here. Okay, now we can easily find the hyperosculating circle with the ellipse in point A by simply also adding the tangent in C and then intersecting this. There we go. Then we need this line and the point where they intersect is here. So drawing the line perpendicular gives us this, and that means that this point here is the midpoint of the circle that we need. This is now the circle. We'll just eliminate all of this other stuff. We don't need this. Don't need any of this. So we know that the ellipse can be transformed to this circle here by means of a collinear transformation that maps B onto this point here where the circle intersects the main axis. I'm going to also eliminate the graph paper background. I don't think we want that right now anymore. This point here is the point that it maps to, so we'll call that point there B prime. Now we'll assume that the point we want to map this whole thing onto a line parallel to a line that passes through B. So I'll just choose a line through B to make this easy enough. And we'll simply say that or rather, no, I'll make this easier because otherwise we'll be running out of time here. So we'll make this simply with just any tangent. Otherwise, we'll have problems with this. I'll just do any tangent of this circle here and just map that onto a tangent of the ellipse. That's easy enough to do in just a few minutes. So I'll just choose any point on the circle. Let's say this point over here. Then we'll find the point, which is maybe over here. Then we'll find the tangent in this point that's perpendicular to the radius. There's the tangent in this point. And now to find this same tangent of the ellipse, we simply need to transform this line onto to the other point set. Now that's straightforward to do because we know that all of the points on the line perpendicular to the major axis through the common point A are all fixed points. So if I determine this line that's perpendicular here, that's this line here, the point in which they intersect, the tangent, this point over here, will be a fixed point. This point will definitely also be a point of the other tangent that we will obtain now, because nothing changes here. But now we have to find what does this point here map to? And that's the interesting question now. What point does this point map to? Now, how do we get this point? Well, we know that it maps onto a point that lies on the line joining this point to the center of the collinear transformation. And the center of the collinear transformation is A. So it lies somewhere on the line joining this point with A. It must be somewhere on here. And also, we can now transfer this point to, if we call it, I don't know, P or something, or P prime, to the relevant point P in the ellipse field by simply joining it to a point that we already know, the relevant point for. And that would mean joining it with B prime. So if I simply connect this point with B prime, I can now transform this whole line into the other point field, into the point field of the ellipse. That's very easy now because I know that the point B prime maps onto B. And I know that the point where this line intersects the fixed point line is, of course, yet another fixed point, this one here. So that means that, oh, I didn't want to join this point. We know that B prime maps onto B. This point is fixed. So this whole line maps onto the line joining these two, joining this point and this point. So that means that this point of tangency for the circle maps onto this point over here as a point of tangency for the ellipse. And that means that the tangent of the ellipse is simply the line joining this point here with the fixed point. And therefore, this point here is the point of tangency for the ellipse, which is, of course, is very close to the tangent in D, but not quite the same. There's a slight difference. I'm sorry that there wasn't time to do this in more detail. Of course, I can talk about these things for hours and hours and hours, but this is more or less what I was hoping to show you these three different approaches to finding elementary Euclidean constructions that can be applied to the ellipse by transforming the ellipse in some way to circles that can then be used for the constructions, and then reversing these applications to get back into the ellipse. I hope it was a little bit interesting for you. I hope you'll be able to use these ideas at some point. I think the concepts that I've shown here have become a little bit non-standard. If we go back maybe 200 years, these were the normal ways to consider elliptical constructions, but nowadays it's considered a little bit exotic maybe, but I still find it fascinating, and it's a very hands-on thing to do, to actually do these drawings with your own hands. I always find these things very enjoyable. As was the case last time I spoke, I have one last thing here. I have some information for you to perhaps use if you're interested, and to thank you for listening to me. You can check out my own website, which is at the top here. And of course, you can check out the website of the University of Vienna, sorry, where there are a lot of these materials that some of the materials that I have developed, but there's a whole team that works on developing materials for all manner of school mathematics, but also Olympiad mathematics. And the link that I specifically have put up here is the link that leads to topics that are applicable to Olympiad style mathematics rather than regular school mathematics. So if you dare to have a look at the stuff that's all in German, of course, but if you don't mind that too much, then I'm sure you'll find a wealth of material there at all levels of difficulty and on all different subjects. So all that really remains now is the last line here. Thank you for listening once again. Thank you for inviting me back after the first talk. And I hope this was as enjoyable as the first.
Thank you very much, Robert. Yeah, we also would have wanted to listen more, but the time constraint really does not help us here. If we had the time, we would also we would want to continue whatever you had to say. Hopefully we'll keep in touch and we can get back on this topic again sometime soon. It was very great listening to you, and it was always, as the previous session was, it was very insightful and interesting, the constructions. Thank you very much. Mathematics Initiatives in Nepal and its team, thank you. Thanks you.
Yeah, thank you for having me.